Hey, good afternoon, everyone. Hey, I tried. Things came up today. I'm so sorry. I've been really rushed, but I'm here. So we are going to finish up the section, the word problem section, where we were talking about exponential growth and decay. Then we did the Newton's law of cooling, and then we were going to start here with, we have just one more type of model to look at, and it's called a logistic model. So before I do it, any questions over anything from last time or anything before that I need to go over, clarify, homework problems, anything? On the homework, I said to take a look at these first few problems here. And then I said there was a few more here that we haven't done. So your homework for tonight will be to finish up these problems 23 and 27. They're both logistic models, which we're going to talk about now. So no questions? Okay. Well, the logistic model is actually one of the most useful mathematical models we have, because when you look at the graphs of these, they do something kind of unique that no other graph does. And that is, the function will have a horizontal asymptote as you go out to the edge, as you go out to the right or to the left. But that asymptote, it's like your function's trying to reach it. It never gets there. We've seen that before, but it's the fact that in the middle, it does the same thing, goes down to the left. You have two horizontal asymptotes instead of one. So everything we've looked at before, you've had just one horizontal asymptote. Here you have two. And out one side, you go towards one of them, and out the other side, you go to the other one. So this is very useful. I'll show you when we get to the word problems. I'll show you, where these are used. But it's like the one that we're going to deal with the most here is this one. It's like what's happening is, as maybe like time goes by, something is growing and growing, but it gets to like a peak where it just can't go past that point. And this is used a lot for like populations. If you think about, if you put like, there's a classic problem where there's like an island, right? You got this island, and on the island you put foxes and you put rabbits, and then you put, grass. And then with those three things, you have like an ecosystem, right? The rabbits will eat the grass, the foxes will eat the rabbits. And so you have this, this interaction between these things. And so when you talk about like the population of each one of these, there is some like maximum population for each of these. Like the rabbits, they can't just keep on growing and growing and growing, right? If they grow too much, then they run out of food. So, there's like a peak to how big that population can get. Also, the bigger the population of the rabbits, the more food for the foxes, right? So the foxes eat the rabbits. So there's some peak. And the same thing goes for the fox, right? All the foxes on the island, if their population gets too big, they'll run out of food. So these logistic models are perfect for situations like this. Some things to recognize. Here's the actual model, the function. You'll notice that it is exponential in the sense that it has an exponential expression in it, e to the negative bt, but it's in the denominator of a fraction, which is unusual. We haven't seen it down there before. So anytime we have something like this, we're going to have one of these two graphs. This first one is if the b is positive, and then the second one is if the b is negative. Now this is tricky. In the formula, b right there, see that b? It has a negative sign in front of it. Okay, so this is saying if b is a positive number, so let's say b was 2, then in the formula it would look like negative 2t. That would be a positive b. I know that seems weird, but b is not, you do not include this negative sign when you're talking about the sign of b. So if b is positive, we're going to have this type of logistic model. And if b is negative, well, then you would have a double negative, and it would look like a positive number here. And that would be this logistic model. So in these logistic models, the important properties, the domain is everything. So you can plug any number you want into a logistic function. You have no restrictions on domain. So it's not like a logarithm where you can't plug negatives in or anything like that. So we have a domain. And then real important here, the range is from 0 to C, not including 0, not including C. So you can see from the picture here that the function tries to reach this value of C. It tries to get there, but never does. And on the bottom, it tries to get towards 0, but it never does. So as it approaches this value C and it never reaches it, we call that the carrying capacity. This would be like if you're talking about the rabbits, the C would be like the maximum population we could ever reach with the rabbits. It's the carrying population. How much can this situation, how many rabbits can be carried within that system? So that C, that number C that it's approaching, it's called the carrying capacity. There's no x-intercepts on a logistic model, never hits the x-axis. The y-intercept is always p of 0. So it's what you get when you plug 0 into the function, right? That's that point right there and that point right there. And let's see, it's an increasing function if b is greater than 0. So that's this scenario. As you read it from left to right, it goes up. And it's a decreasing function if b is negative, so it goes down. Now, there's a point in a logistic model. There's a very special point. You'll actually hear more about this point in calculus. It's called the inflection point. And in this graph, the inflection point's here, and it will always happen when you're at half of your carrying capacity. So inflection point is a weird idea, but I can try and get you to see it maybe. If you look at this graph on the left, to the left of that inflection point, the graph looks like it's part of a smile, right? Like if you write a smiley face, a smiley face, this to the left of this point, it kind of is part of a smile. But if you get to the right of that inflection point, now you're looking more like a frown, right? So an inflection point is always where you have this change from a smile to a frown or a frown to a smile. Again, that's more of a calculus concept. Here, we just need to understand that for a logistic model, the inflection point always happens. The Y value of it is half of the carrying capacity. Okay, that's pretty much it. I think we're ready. We've got the basic idea here. Let's look at a problem. So fruit flies are nasty, right? If you've ever had fruit flies in your house, or my buddy used to own a bar. Fruit flies are always really hard to contain. Fruit flies are placed in a half-pint bottle of milk with a banana for food and yeast plants for food to provide a stimulus to lay eggs. I'm not sure who's running this experiment. Doesn't sound fun to me, but we've got this situation, right? Fruit flies in a bottle. So suppose that the fruit fly population after T days is given by this. So we look at this and we have to recognize that this is a logistic model, right? We have to see, hold on. Erase all that. So we have to see that it looks like this. And they're giving this to us, okay? They're giving us that we have a logistic model here. I think that's as good as I'm gonna be able to do right there. So for us, when we look at this, let's identify some things here. The number on top, right? That's our C. That's the carrying capacity for this situation, which means that the maximum number of fruit flies we could ever expect would be 230. Actually, we'd never get to 230, but we couldn't go past it, right? So in this situation, 230 fruit flies is the max we can have there. Let me see, what else do we have here? What's B for us? Can you tell what B is? This is where I said it's a little tricky because you have to, the B here in the formula has a negative in front of it. So ignore this negative, right? And the B would be just the 0.37, right? That would be B. So for us here, B is positive because B is 0.37. I'm just identifying some things here. That you should be able to see right off the bat. So once we know that this is positive B, if we go back and look at the notes here, if B is positive, we should see this sort of function right here. Now I'm going to graph it just so we can see it. All right, got a graph here ready to go. Actually, I need to change. Let me just hide this. Hide that. So it's 230 over 1 plus 56.5. And then times e raised to the negative 0.37x. Okay, here's our logistic model. So we should expect that carrying capacity to be 230. So I need to go way up on my y-axis to 230. That's where I'll see it peak off like this. And I'm going to adjust this a little bit, just so it looks a little different. 50 here, too much. 50, there we go. And let's go negative 26, negative 2. There we go. That's probably more like it. Okay, so you can see we have an initial population here of fruit flies, and then the population starts to grow with respect to time, and it tries to get to this 230. It's never going to get there. All right. So that's the visual situation. Let's answer some questions here. So first part, state the carrying capacity. We've already done that, right? 230 fruit flies. And the growth rate. The growth rate is the B. All right. So I think I failed to say that here. Growth rate. Where does it say it here? It doesn't say it anywhere, does it? Okay, they don't even state it here, which is weird. The growth rate is B. Okay, so for us, the growth rate here is the 0.037, and it was positive, right? All right, so what is part B asking for? To determine the initial population, what do we need to do?
Set t equal to 0.
Equal to 0, right? So t here is the number of days. So if we want to know the initial population, we want to know what's happening at the beginning. So we want to take 0 and plug it into the function. Let's do that. 230 over 1 plus 56.5 e raised to the, well, what happens if I plug in 0 for t here? It's just going to 0 all that out, right? And so we just have e to the 0. And what's e to the 0? Anything to the 0?
1.
Okay, so e to the 0 is 1. So now I just take 1 plus 56.5. So 230 over 57.5. And we'll get our calculators out. May or may not go in there evenly. 230 divided by 57.5. Oops. Oh, 4. Okay. It's a perfect integer. So 4 flies. So we started out with 4 flies in that container. That's when we started the clock. And now they're going to start to grow and they're going to peak off. They don't have any predators in there, right? What is the thing that's stopping their population growth?
Food?
Why doesn't it just take off? What's that?
Their food?
They have a restricted amount of food. They also have a restricted amount of space, right? I mean, they do need some space to live, right? So there's a food restriction. There's also a limit as to how many eggs they can lay at one time, right? Some of them are going to die. There's a max population in there. Now you have to remember, this is a model. This is not like a perfect, like it's not going to be so accurate that you can count on it, exactly to tell you everything that's happening, but it's a model. And that's what we do in the real world. We take a situation, we try and find a mathematical representation of that. The logistic model is the best representation we have for a situation like this. So we start with 4 flies, right? Okay, what's the population after 5 days? Well, all we have to do there is plug 5 in, right? Because we're measuring things in days. So this we'll definitely need a calculator for. We're gonna go 230 over 1 plus 56.5 e to the negative 0.37 times 5, like that. So this is not like what we're doing here is not crazy, all right? We just need to be able to get this on our calculator. So I'm going to do right now the e to this power on my calculator, just so I can get that answer. And so I have here 230 over 1 plus 56.5. And then e raised to that, I got 0.1572. I'm going to go 4 decimal places. And then I multiply that, 0.1572 times 56.5. And then I'm going to add the 1. So I'm doing all of the denominator now at one time. I get about 9.8818, something like that. And then I'll take 230 and divide it by that. And you're going to get approximately 23.2728, something like that. About 23 flies. So after 5 days, you should expect to see about 23.2 flies. So about 23 flies or so. Again, it's not perfect. It's just, you know, some sort of representation of what's going on. If we go back to our graph, I can actually trace this out. After 5 days, yeah, you can kind of see there about 23.27, something like that. And then it's going to continue to grow and grow and grow. So what's the next question asking? How long does it take for the population to reach 180? So now instead of them telling us, you know, how long, you know, instead of them saying how many flies are there after a certain amount of time, they want to know how long it's going to take to reach to 180. So this time for part D, we're going to take the equation, the formula, and do what with it? T. What are we gonna do with this? We want to know when that's equal to 180, right? So set it equal to 180. This is more challenging than the previous problem. Part C, you just plug a number in, you crank it out on your calculator. Here, we actually have to go and solve for T. All right, we're gonna have to go solve for that now. So we've got to do some algebra. Any questions on what I'm trying to do? Everyone clear on what I'm about to try? Get T? Anyone have an idea of how we can get T?
Start by clearing the denominators.
Clearing out the fractions, good. So I'm going to multiply the whole left side by the denominator. And whatever I do to the left, I have to do it to the right. Now, the reason we did that is because it gets it off the denominator, like gets it out of the denominator, leaves us with 230 on the left side. And on the right side, we have 180 times this thing, right? So it cleared the fractions. So that's where we are. So I am not going to distribute this 180 through. You could do it, but I'm going to divide both sides by 180 right now. And that will clean it up on the right-hand side. On the left-hand side, well, I'm going to get a decimal. I get 1.278, let's say, equals. Now I don't need the parentheses anymore because I got that 180 out of there. Okay. And now it's just a matter of, now we've got it to something we've seen before. This is an exponential equation. we're going to try and solve for t. So we've got to get that e thing by itself. So I'm going to subtract 1 on both sides. So that gives me 0.278 equals 56.5 e to the negative 0.37 t. What next? Trying to get this by itself. Divide through, right? Get that 56.5 out of here. So we're going to start getting some small numbers here. 0.278 divided by 56.5. I get 0.00492 equals e to the negative 0.37 t. Finally, we have the exponential isolated. So here's where we bring in the log. All right, so here comes my log. It's going to be log. The base of that is e. The other side is the negative 0.37 t. And then in here goes the 0.00492. And then from here, I just need to remember that log base e is natural log. So I can just immediately go to natural log of 0.00492. I'll do that on my calculator. And so I'm going to do natural log of 0.00492. Okay, so I get negative 5.314 is equal to negative 0.37 t. Last step, divide both sides by negative 0.37. So I'll take that, divide by, I get about 14.36 is t. About 14 days. Okay. Any questions there? Would you all agree that part D is a lot harder than part C? I mean, in the sense that there's a lot more algebra to do here, lots of room for mistakes, whereas part C, you're just plugging a number in, right? Same with part B, just plug a number in. Now, we're not going to do part E, and on your homework, you can skip anything that has a picture. This is a picture of a calculator. This is saying to use your calculator to do this. It says use a graphing utility to determine how long it takes for the population to reach 1/2 of the carrying capacity. So half of the carrying capacity would be 115, right? That's what it's asking. How long does it reach to take 115? So I can actually do it here. All we're doing is looking at the y value of that point, and we're trying to see where it's 115. Right around, say somewhere in here, right about there. Looks like about 10.9, about 10 or 11 days, right? 10 or 11 days is what it would take to reach half of its carrying capacity. And then the problem we just did, it wanted to know how long it took to reach 180. So let me go up to 180 here. You see 180 was about 14 days or so. That's what we got, about 14 or so days. Understand? Any questions about the picture, the function? Does it all make sense? We have another one. All right, so for this one, it's talking about wood. Wood products are classified. Well, there's this industry standard for classification of wood products according to their lifespan. And there's 4 classifications: short, medium, short, medium, long, and long. This is how long wood products will last. Based on the data obtained from the European Forest Institute, the percentage of remaining wood products after T years for wood products with long lifespans, such as those used to make buildings, is given by this logistic model. So the first question here is, what is the decay rate? So they want to know what B is. So can you tell what B is here? I mean, so I should have said
Negative
this is legit.
0.05.
Say again, Hugo?
Negative 0.05.
Yes, exactly. So we're looking at that number in front of the T here. We notice that it's a positive number, right? But in the formula, that's supposed to represent negative B, right? Negative B is that number in front, 0.0581. So B for us must be negative 0.0581, which means we have a decay rate of negative, right? Negative 0.0581, which as a percentage would be about 5.81%. And it's decreasing, right? So decreasing by 0.0581. Okay, what is part B asking us to do? What's part B?
Set the time to 10 years.
Yes, set time to 10 years. So plug 10 into the function, which I think most of you would probably be okay doing. Yes, just plug 10 in there. Get your calculator and do it. I would like to see if you can take the next 5 minutes. Maybe I'll give you maybe 5 to 8 minutes to see if you can do part C. Now, I want to make sure you understand what this formula, right? This formula that they're given, what it is it gives the percentage of remaining wood after T years. So this left side is the percent that's remaining, right? The percent that's remaining. So on part C, we want to know when this equals what. This is tricky. That's why I don't want you to go too far before I explain this. They want to know how long it takes for the percentage to reach 50%. So what am I going to set this thing equal to? 50 or 0.5? What do you think?
$50.
Okay, so why 50 and not 0.5? Because I thought we always converted percentages to decimals.
Because it's half of the max, which is 100.
Yes, I agree. Oh, okay, all right, there you go. Okay, so that's where you can get this from. You look at your 50%. Hold on. I'm going to say yes and no. Hold on, because I want to make sure I'm understanding what you're saying. You're saying take half of the carrying capacity?
Yes, sir.
Okay. What do y'all think about that? Half of the carrying capacity. Would half of the carrying capacity be 50? Or would it be 50 with some stuff?
No, it'd be 50.
50 and some change. I would say it's 50. I
Yeah,
agree.
because half of 100.3952. So let me back up. Let me do this. What's P of 0? What would happen if you plug 0 into this? Let's see what we get. Just plug 0. When I plug in 0, that would give us the percent of the remaining wood, right? At time equals 0. Plug it in, see what you get. So if we plug in 0, we get 100.3952 over 1 plus, okay, when you plug in 0 for E, all you're going to get is a 1 there. So you get this 0.0316. Add those together. Divide that. Make sure I type that in right. So 97.319. Did
So
anyone else
that's
get that?
basically 100%.
Say again?
Is that 100% and you get half of that?
Yeah, so this is what we have to, this is why I want to make sure you understand this. So what this formula spits out, right? When you plug in a value for T, it spits out a number and that number represents the percentage, right? So at the very beginning of time, right? At the beginning of this, we have 97.39%, all right? So the output of this function is the actual percentage, not the decimal form. It didn't, if it would have spit out 0.97, right? Then we would say, oh, okay, it's measuring it with, we still have to move the decimal over and convert to a percent. That's not what's happening. With this function, it is actually spitting out the percentage already moving the decimal. 97%, 97.319% remaining at the beginning. With me? So how long, it's asking in part C, how long does it take for the percentage of the remaining wood products to reach 50? So one idea was to say, okay, take this number, right? And just cut it in half, divide that by 2, right? That would be half of the carrying capacity, wouldn't it? That's half of the carrying capacity. That's not what we're looking for, though. We're looking for, we would have to, the only way we could do that is if in the beginning it was 100%, I mean, beginning was 100%, and it's not. At the beginning, it's 97.3. So what we need to do instead is we need to take the function P of T and set it equal to what?
50.
50. Not 0.5, but 50. Do y'all get what I'm saying? I mean, I understand, I like the idea of taking this and taking half of it, but that's not the question. The question is to not take half of the carrying capacity, but to figure out when the function spits out 50%. So take a few minutes. I want to see if you can do this. And you know what? I'm going to put up a poll in a second. I'm going to put up a poll and I'm going to see if I'm going to give you choices for the answer. And I want to see if y'all can get it. How many of you get it right? So you're going to take the original function and set it equal to 50 and solve. Take some time. Make sure you can do this by hand. Don't just use a computer. I want to make sure you know how to do this during the test, okay? Okay, I just launched a poll. The poll has 4 choices, and I gave you the 4 choices here. We have 1 student response so far. We'll go a few more minutes.
I need just like a couple more minutes.
Yeah, take your time. I'm going to give you time. All right, we've got 2 students that have answered, 3 students have answered now. Four, 5. See if maybe we can get 1 more. Okay, I think that's probably enough time. So let's see, how do I stop this poll? Where's the button? Went away. Oh, there it is. Okay. All right, so you can see the results. 80% of you chose C, option 3, I mean, and that is correct. It is 3. So what do you think? Should we move on, or do you want me to go through it? Most of you got it. I'd say for anyone who didn't get it, why don't at the end of class, if you want to talk about it, we can go through it step by step. Sound okay? That does it, okay, for this section. Your homework, you've got these 2 logistic problems. Again, I would skip the parts that have the calculator next to them, skip that. All right, skip that. All right. See how you do with those. And that wraps up this section. Okay, we're ready to move on. All right, we are jumping now all the way to the very last chapter that we're going to talk about. I believe, if I'm not mistaken, this is on our schedule. This is the last, chapter 13. There's a few things from chapter 13. So yeah, that's if we can get to it. All right, we'll try and get this chapter 13 in. Chapter 12, though, we're going to be doing something, like I said, very different than what we've been doing. All right. So a big shift of gears here. We pretty much are done in this class with the different types of functions that we wanted to look at. We looked at lines in the very beginning, then we looked at parabolas. After parabolas, we looked at polynomials. After polynomials, we looked at rational functions. After rational functions, we looked at exponential. Then we looked at log. Now we've looked at some models involving exponentials. you know, with the growth decay, the Newton's law of cooling, and then finally the logistic model. So we are done with functions, no more, all right? We are now moving on to a different topic, solving systems of linear equations, all right? So here's the way I'd like to motivate this. Let's go back to the very beginning of class when we had something like this, y equals 2x plus 1. Now, we all know what this is, right? If I asked you to graph this, we all know that this is a line, right? And if you went to graph it, it would be actually pretty easy because I already solved it for y. So to graph it, all you'd have to do is go to the y-intercept, which is 1. Remember, this looks like mx plus b on the right side. So you go up 1, put a dot, and then you'd use the 2. That's your slope, your rise over run. So you go up 2 to the right 1. You draw a point, connect the 2 points with a line, and you've got the graph, right? Great. Now, what if I gave you a different equation? Y equals negative 3x, let's say, plus 4. Okay. I ask you to graph that. Well, you can do the same thing, right? So you go up 4, I'll count by 2. 2, 4, you go up 4, you put a dot, and then you go down 3 over 1. Down 1, 2, 3, and over to the right 1, and then you draw a line through those 2 points. So graphing lines individually, we know how to do. No problems, right? It's all good, hopefully, yes. So what I want you to think about is what each of these points on these lines represent. Each point here, like that point right there is the point 0, 1. This point right here is the point 0, 4. What those points represent are solutions to this equation. Meaning if I plug in 0 for x, so if I take that equation and I plug in 0 for x and 1 for y, this should be true. So let me replace the y with 1, replace the x with 0, and you get 1 equals 1, and that is a solution. What's this point up here? What are the coordinates of that point? Well, how did I get there? I went from here, I went up 2 and over 1. So what would the x coordinate be? If from this point I had to go up 2 and over 1. What is it? Sorry, I didn't hear you.
Wait. Would be 3, 1?
3, 1, 3, 1, 3. So the y coordinate goes up, you add 2 to the y coordinate, right? So that becomes a 3, and then the x becomes a 1. So to the right 1, up 3, right? That should also be a solution to this equation. If I replace the y with 3, replace the x with 1, then I get 3 equals 3, and that's true also, right? And that's what the line represents. Every point on this line, every single point that you could ever pick should go into that equation and should give you true, right? It should give you a true statement, true equality. Same with all the points on this line, right? They should go in, you plug them into here, any point here, you plug it in there, and it should be true. My question now is there an x and a y? Okay, is there an x and a y that would satisfy both of those equations at the same time? So like it, you know, like this point 3, this point 1, 3 that we just did, it plugged into there and it was true, but would that answer work here? We could try it, right? We could try, let's see, if we replace the y with 3 and we replace the x with 1, is it true? Let's see, 3 equals negative 3 plus 4. That's not true, right? That's not true. So even though this point is a solution to that equation, it is not a solution to this equation. Is there a point though? Is there a point that would solve both of these at the same time, give you true statements at the same time? What do y'all think? Do you think that that a point exists that would solve them both?
Yes, because
Yes.
they aren't parallel, so they have to intersect at some point.
Okay, so you're saying that yes, because if you drew both of these lines together on the same graph, right? If I took that first one, we started at 1, we went up to over 1, we drew a line. That was our first line. And our other line, we went up 4, 1, 2, 3, 4. And then to get to another point, we went down 1, 2, 3, and to the right 1. And now we draw this line like this. And what you're saying is because these lines aren't parallel, they hit each other, there is a point that is on both lines. And that point should be the point we're talking about, right? Because whatever that point is, since it lies on both lines, it actually satisfies both equations simultaneously. That's what a solution to a system of linear equations is. It is a point of intersection of both lines, all right? So given two lines, we try to find a point of intersection. Will we always have an answer?
No,
Okay, no, when would we not?
when the lines are parallel.
If the lines are parallel, right? So there are actually 3 cases we can have. There are 3 cases we can have when we're trying to figure out whether or not there's a point of intersection. The first case is there is a single point. Okay. Second case, there's no point of intersection. This would happen if the lines were parallel to one another and the lines are what we call distinct, meaning they're different lines. The third possibility is every point is a point of intersection. And that would happen if they are the same line. So if I give you a line and then I give you the same line and ask you where does it intersect, it would be everywhere because they're the same line. So those are the only 3 possibilities. In the 2 cases that we have here where we get answers, right? In those 2 cases, we actually have answers, right? And in the second case, we have no point. That means there's going to be no solution. So how do I go about telling you, I want you to go do this, right? I could write out like, hey, look at these 2 lines, find the point of intersection. But the way we do it, we use a certain notation for it. Now, I'm going to go up here and grab these real quick because I need them. So here's the notation we'll use. I'll erase that in a second. What I'm going to do is I'm going to put a brace, and then I'm going to write the equation of the first line. And then I'm going to write the equation of the second line. And that right there is what we refer to as a system of linear equations. And when you write that brace in front like that, when you write that, what that is telling you is to go find the point of intersection of those 2 lines. You're either going to find a single answer or no answer, or you're going to have an infinite number of answers. But the brace is what tells you you need to solve these simultaneously, find a simultaneous solution. Now, when we look at this, I want you to notice that we have 2 equations, right? Do you all agree we have 2 equations? And we have 2 variables, or what we call unknowns. So we have two equations, the first equation, second equation, and then we have, within these equations, we have two variables, x and y, x and y. So there's two equations and two unknowns. That's all we're going to talk about today. Next class, we're going to have three equations, three unknowns. And then you can keep going, four equations, four unknowns. But the geometry changes. When you have three equations and three unknowns, you're not looking at lines anymore. You're looking at something else. And we'll talk about that next class. Let's focus just on this scenario right now, today. All right, so how do we solve this? So how do we solve this? Well, one way would be to, draw the graphs and then go try and find that point, right? Just by looking, by visually inspecting it. There's a problem with that though. Your graph has to be very accurate because you need to be able to tell me what that point is. And sometimes that point's it's not possible for you to visually tell me from the picture. So we need an algebraic way of doing it. We need some sort of algebraic way to do this. And there are two methods that we use to solve this. And the good news is you get to choose. I'm going to show you both. You pick the one you want. I have my preferences, but the two ways we have are, the first method's called substitution. And the second method is called elimination. And what I always tell my classes is do not marry one of these, okay? Don't get married to one of these methods. Like, be willing to use both, because sometimes substitution is better than the elimination. Sometimes elimination is better than the substitution. And because a lot of students they'll just be like, oh, I really like substitution, I'm gonna do substitution. And then they just totally don't even pay attention to elimination. The problem with that is when you get to three equations and three unknowns, or four equations and four unknowns, substitution is terrible. It's not the way to go. Elimination is more powerful. So although substitution might be nice, you might like it, please keep yourself open to elimination, all right? So here we go. How do we do substitution? There are a set of steps. I'm gonna do each one of these one at a time. So for substitution, there is a set of steps, but it's kind of hard to, you can write the steps down, but it's still kind of hard to have like precise steps. I'll do my best. We're going to do this with substitution. All right, so what are the steps for substitution? Well, the first step is you choose one of the equations and solve it for either variable. So you get to look at the equations and you say, okay, I'm going to look at the first equation and solve it for x, or I'm going to look at the first equation and solve it for y, or you can do the second equation, solve for x, second equation, solve for y, your choice. Okay, that's the first step. Once you do that, okay, you've taken one of the equations and you've solved it for one of the variables. Now what you're going to do is you're going to replace that variable, or if you don't want to use the word replace, we'll use the word substitute, which is where it gets its name from. Substitute your answer from part one, which is the part you just did, into the other equation. Once you do that, solve that equation. Once you solve that equation, you will substitute that answer the answer from the third part that you just did into part one. Okay, like I said, when I write the steps out, it seems weird. Let's just do it, all right? And when we do it, it'll make hopefully a little more sense. All right, so I'm looking at the system of equations. And I'm saying to myself, okay, I need to pick one of these equations and solve it for one of the variables. Well, the good news is that both equations are already solved for y, aren't they? They're both solved for y. So my first step of picking an equation, really there's no bad way to do this. I'm just going to pick the first equation and I'm going to solve it for y, which it already is solved for y, right? So I'm done with step one. Step two, replace or substitute the answer that we just got into the other equation. So now what I'm gonna do is I'm gonna take that other equation, which was this, and I'm going to replace this y with the answer I got from part one. So I'm gonna take that and put it in here. So I replaced the left side with 2x plus 1, and then equals negative 3x plus 4. Understand? I've made a substitution. Step 3 is to solve this equation. So for step 3, I'm going to solve this equation. And to do that, I'm going to bring all the x's to one side, all the numbers to the other side. So I added 3x on both sides. I subtracted 1 on both sides. And then divide by 5. So x is 3/5. I know what x is now, right? I know what x is. The fourth step is to take that answer, 3/5, and plug it into the first equation. So in the first equation, we had y equals 2x plus 1. I'm now going to replace that x value right here. So we get y equals 2 times 3/5 plus 1. This gives you 6 over 5 plus 1. And with a common denominator, you'll get 11 over 5. Because that's 6 over 5 plus 5 over 5, right? Get a common denominator between these two, and you get 11/5. So now you know what y is. So we have a solution. It is 3/5, 11/5. That's your x and y coordinate. Okay, questions? No? I'm going to go to the graph. I'm going to graph these real quick for us, just to verify that we did get the right answers here. So the first one was y equals 2x plus 1. Okay, there's the graph. And then the other one was y equals negative 3x plus 4, right? Those are the two lines. And the computer is actually smart enough to find that point of intersection. 0.6 and 2.2. So if you take 3/5 and convert it to a decimal, 3/5 is the same as 0.6. And 11, what was it, 11/5? 11/5, right? Yeah, 11/5 would be 2.2. So I know you may be sitting there going, why would we go through all this trouble if I can just use a computer to do this, right? I mean, the computer did that really quick. And I would agree with you. Like for a system of 2 equations and 2 unknowns like this, the computer is really helpful. It's when we get to higher, like 3 equations, 3 unknowns, this doesn't work because, well, at least not yet. We don't have computers, or we don't have easy ways on a website to just go do it with 3 equations, 3 unknowns. Because when you have an equation with three unknowns, x, y, and z, your picture is no longer a line, it's a plane, it's a flat sheet of paper. So it's 3-dimensional. And so we don't really have that ability yet. Actually, we do have the ability, but Let me see. I'm going to see what this does. I doubt this is going to do it. Let me see. I haven't been here in a while. Graph, if I want to do a 3D graph, if I do x plus y plus z equals 1 equals 10, where is it? Oh, there it is. Okay. Whoa, whoa. That's pretty cool, huh? I can graph a plane, and then let me graph another one. Negative 2x minus 4y plus 6z equals 12. There's another plane. See if I can change the color. I'm sure I can. I'm not going to mess with it. But now we have 2 planes. You see that? That would be 2 equations. Let me add a third equation here. Negative x plus 5y minus 4z equals 4. There's a third plane. And so when you're trying to solve a system of 3 equations and 3 unknowns, you're trying to figure out where all 3 of these planes hit each other. And you see that the computer's not allowing me to do that, although there is a tool. I can find the intersection of 2 surfaces. There we go. There. It can do all this computer can do is it can find me the it can find me why is it not letting me turn it now? Oh, there we go. So it can find me the intersection of 2 of them at a time. So it can give me where 2 of the planes hit each other, and they hit each other in a straight line. I'm trying to figure out where all 3 hit each other. And this software, as great as it is, this website is just not capable of doing that yet. All right. I mean, there's ways you can have a computer solve it, but not visually, not real easy, not like what I did before just a second ago, graphing the lines. So if you're sitting there going, hey, in the real world, if I become an engineer or whatever it is, if I ever need to solve a system of 2 equations and 2 unknowns, I just go to a computer and do it. I would say, yes, go do that. Don't do it by hand. You're going to make a mistake. You'll probably mess up something. Use a computer, right? But it's for the higher dimensional stuff that we need to have some method in place. All right, that's substitution. We'll do more examples, but now I'm going to do the same problem using the other method called elimination. Let me take that same thing. I'm guessing that some of you in here have seen this before, all right? I'm pretty sure this is covered in algebra in most, well, it depends. Elimination. Okay, so elimination, what are the steps? First step, move variables to left. Numbers or constants to the right. Now, when I do these steps, I'm going to do this. I'm going to do the step, and then I'm going to go back to like what the method is and back to the step, because elimination is really hard to write the rules or what you're doing, okay? Or what the goal is here. So first step, I'm going to take this and I'm going to rewrite these equations. I'm going to move all the variables to the left side and any numbers to the right. So all I did here on the first equation is I moved that 2x to the left, which made it a negative 2x. Then on this one, I'm going to move the negative 3x to the left, make it a 3x plus y equals 4. Okay, everyone understand that first step? Just move everything over. Also, make sure that you've lined up your x's and your y's. So your x's are on top of your y's. Don't do one of them where the x is first, then the y, and the other one is reversed. Make sure it's x, then y, x, then y. All right, you with me? Now what I'm going to do is I'm going to look at the x's, and I'm going to see if there's any way I can make these x's cancel with each other if I were to add these things straight down. So right now, if I added this down, negative 2x, add 3x, that would not make the x's go away, right? If I added straight down, it would just become negative 2x plus 3x, that would be x. What about with the y's? If I add straight down, y plus y, they give me 2y. That still doesn't make it go away. So I need to look, is there an easy way to make these go away? And what I realized that the y's are really, they would go away if one of these was negative, right? Like if one of these was a negative y, then if I added them together, the y's would go away. So I'm going to make one of them negative. And so what I'm going to do is I'm going to take the first equation and multiply it by -1. So think about this. If you have an equation, you can always multiply both sides of the equation by any number you want, right? So if I multiply the entire equation by -1, both sides, it's the same equation. I'm just changing what it looks like. So I'm going to multiply through by -1. I should get a 2x minus y equals -1. And then the bottom equation is 3x plus y equals 4. That is a legal move. I'm allowed to do that. All I did was multiply the first equation by -1. Now add straight down. Okay, take these two equations and add them down. So if you add 2x plus 3x, you get 5x. You add the y's together, they go away. And then you add this together, -1 plus 4 gives you 3. And now look at this equation you have, 5x equals 3. And you can solve for x. X is 3/5. That's the same answer we got before, isn't it? It's the same exact answer. The next step is that you're going to take this answer and you're going to plug it in to any equation you want. Any of those, you get to choose. Doesn't matter. You can't go wrong, all right? You can pick any of those and replace x with 3/5. So I don't know. I'm just going to pick this one. All right, so if I do 3 and I replace the x with 3/5, and then I add y, that should equal 4. I multiply 3 times 3/5, that gives me 9/5, plus y must equal 4. And I'm solving for y now. I subtract 9/5 on both sides. And then I get a common denominator here. 20 over 5 minus 9 over 5. And that gives me 9 over 5. And that gives me 11 over 5. Which is the exact same result I got before, right? So what do you all like? I mean, out of the two I just did, which one seemed to be better to you? No comment? Elimination? I like the elimination personally. This one just to me just was cleaner. Okay. Questions? I'm going to do another one. All right, so you're looking at a system of linear equations. We have 2 equations, 2 unknowns. If we do substitution, right? If we do substitution, then we would have to take one of these and solve for x or solve for y, which I think both of these would suck to solve for x or y because you'd have fractions. But elimination looks to me like it might be preferable, right? Because look at your x's. Could you make these go away? What would you have to do to make these go away?
Multiply by 2.
Multiply the first equation by 2, right? I multiply the first equation by 2, that would turn that into a 10x, and that would cancel out with negative 10x. So I have to do that to all of this. So I rewrite the system.
But
10x.
wouldn't that cancel the y2?
Yes, let's keep going. Let's keep going. Negative 6y, right, equals 24, right? And on the bottom, we have negative 10x, nothing changed on the bottom, plus 6y equals 15. And now add down, right? Add these down. So you add down there, you get 0, plus now you add here, oh, the y's went away also, right? Equals what? Add down, right? 39. What? 0 equals 39. What the hell's going on here? 0 doesn't equal 39. What's going on? Did we mess up? What do you think?
The lines are parallel.
Yeah, so remember we said that there are 3 scenarios that could happen, right? Where is it? Right, we're saying, hey, there's 3 different cases, right? One case is that you're going to have a single point. That would look like this. You have 2 lines that hit each other somewhere, and you got an answer. Then you have no point. That would be if they're parallel lines, right? 2 lines that are parallel, they should never hit each other. And then this last one is if you had the same line drawn right on top of itself again, right? Then you'd have all points would be an answer. Look at what we got here at the end. We got this statement here at the end that is not true, right? This is telling us something's going on. 0 doesn't equal 39. This is the case where you have no solution. This is the case where these were parallel lines. So this right here tips you off. You say no solution. All right, no solution. Let's do another one. How about this? X minus 2y equals 10. And then let's go with 2x plus y equals 21. You know what? Hold on. Sorry, I messed up. Yeah, hold on, I have to fix this. Negative 2x plus 4y equals negative 20. There we go. Try elimination. Try and make the x's go away. How could you make the x's go away?
Times 2.
For the top by 2.
Top by 2 again. All right, let's do it. Boom, boom, boom. What would happen? We get 2x minus 4y equals 20. And then the bottom one is negative 2x plus 4y equals negative 20. And do you see how this is almost like the previous one?
Everything cancels out.
But everything goes away. So you're here, you're getting 0 plus 0, right? Equals what? 0, which means 0 equals 0. And that's true, right? Something here is happening, right? Like in the previous problem, this one here, when we did all this, we got a nice answer for X. We took that answer, we got an answer for Y. We had a single point of intersection. On the next example I did, hey, we got something weird. We got a statement that didn't make any sense. Oh, this is where the 2 lines are parallel, but they're distinct lines. They're not the same line, so they never hit each other. And then this one, all the X's and Y's went away, and we got a statement at the end that was true all the time. 0 is 0. So that means these should be the same line. These 2 lines are the same lines. So there's an infinite number of solutions here. Every solution that is a solution to the first one is a solution to the second one. All right, now I'm almost done with this part of it. I want to go back real quick in the notes. When I was talking about the cases here, I said in these two cases that we get answers, whenever we have actual answers, whether it be one answer, an infinite number of answers, if we ever get an answer, we will say that the system is consistent. A consistent system has answers, all right? If we get no answer, it's inconsistent. All right. I want to just look at your homework here. I want you to try the odds for this. I don't care if you use substitution or elimination. You do whatever you want. Solve these. If the system has no solution, state that it's inconsistent. It also asks you to graph the lines. You don't need to graph them. Right? So don't worry about graphing. If you want to use a graph like a computer system to graph them just to check your answers to make sure they look right, you can, but do these by hand. All right. Questions? So I have two things that I want to try and do in this last 20 minutes. So have I told y'all, I feel like I have, but maybe I haven't. Have I told y'all the story about Gauss, the kindergartner? No?
No.
Okay. So this method of elimination that we're using here, this elimination where you multiply and then you add down and doing all this, this method of elimination was actually developed by a mathematician named Gauss. And technically it's called Gaussian elimination. But there's a really cool story about Gauss that I want to share with you. This is like a fable, right? No one's been able to like really truly determine whether or not this story is true, but here's how the story goes. Let's look up Gauss. I want to tell you a little bit about when he lived. Gauss. See, Gaussian elimination is one of the first things that comes up. Leave the page. I forget his first name. I think it's Wilhelm, but Friedrich. Friedrich. Okay, that's Carl Friedrich Gauss. So Gauss lived, we'll go to our trusted Wikipedia. Let's see, born 1777 and died in 1855. So just a few years ago, right? So there's a portrait of Gauss there. All right. So here's the story of Gauss. Back when he was in like kindergarten, this would be like way back, you know, think of kindergarten level. What age is that? What age is kindergarten? I don't even know.
5.
Is it 5, 6? Okay, so 5 or 6. Let's just say he's about 5 or 6. Here's how the story goes. And I should preface this with his father was an accountant. And so there are stories of where when Gauss was very young, 2, 3 years old, he would be sitting on his dad's lap while his dad was doing the accounting. And they didn't have like Excel and computers. They were doing all the accounting by hand. And he would have these columns of numbers and his dad would be adding them up. And Gauss could actually do all the arithmetic in his head before his dad could do it. That's the story, right? Well, okay, Gauss gets to like kindergarten, right? And back in the day, think way back in the 1700s, they didn't have paper that they wrote on in class. They each had like a little slate tablet, like a little chalkboard, and that's what they would write on. So the story goes that he went to class, and the teacher that day told the class, "Hey class, I want you to do this. What's 1 + 2 + 3?" And so the students sat there with their little slate tablets, and they got their answer right, 6. This isn't a trick question, 6. Right? And then teacher's like, very good, very good, very good. Okay, now I want you to do 1 + 2 + 3 + 4. And so they did 1 + 2 + 3 + 4, and they got 10, right? And they're like, okay, great. And then the teacher said, okay, now what I want you to do is I want you to do 1 + 2 + 3 + 4 plus, and I want you to keep doing it until you get to 100 and figure out what that is. And so the story goes that the teacher, I guess that day was having a bad day, didn't want to deal with the kids and just wanted to give them some busy work, right? Like that'll keep them distracted for a while. So the teacher tells them, and then all the little kids start trying to add up all these numbers all the way to 100, right? And within a few minutes, Gauss takes his little slate and he turns it over and he sits there like this, crossed arms, because back in the day, back in 1700s, they also had like discipline and respect. So the kids would just, shut up and sit there, turn the slate over, let the teacher know they're done, and just sat there. And so the teacher notices Gauss, turn the slate over, walks up to Gauss, right, turns his slate over, and this is what Gauss has written down. N times n + 1 divided by 2. And the teacher looks at that and goes, where'd you get that from? And Gauss is like, I just came up with this. And the teacher's like, no, you didn't come up with that. So let me tell you what this is first. This is a formula that will do all this for you. All you have to do is figure out, like, all you have to tell me is what n is, and n is always the last number in the list. So let's just check it real quick. Here, n is 3, right? So let's plug 3 into this formula. 3 times what? 1 + 3, right? So 3 times 4. Take that, divide it by 2. That's 12 divided by 2. That gives you 6, right? That's 6. Now, if you do 4 in there, you go 4, then you multiply times 1 + 4 is 5. Divide that by 2, and you get 20/2, and that's 10. And that's this number, right? Looks like it works. Now, just because it worked twice doesn't mean it works forever, right? I mean, that's just, maybe it's a coincidence, but it does work forever. And the formula was known already, okay? So Gauss was not the first person to ever come up with this. So when the teacher turned it over and saw the formula, the teacher knew the formula, okay? The teacher knew the formula. I was like, where'd you get that? And he's like, Gauss said, well, I came up with it. And the teacher's like, you're lying to me. Who showed that to you? And the teacher got really upset with him and blamed him for lying to him and took him to the principal and all this stuff. And Gauss got in trouble. Well, Gauss had to sit there and show how he came up with the formula, all right? He had to demonstrate it. So I'm going to show you how he did it, all right? And I think when I show it to you, you're going to go, well, that's not so bad, okay? I mean, like, what he did isn't so bad. So check this out. This was Gauss's logic, all right? This is the way he explained it. He said, you want me to figure out what 1 + now I'm talking like I'm Gauss. I'm sure it sounded different coming from Gauss, but he said, you want me to add up 1 + 2 + 3, and you want me to go all the way out to 100, right? Well, Gauss said, I'm going to call that X. Now, I don't know if he called it X, but he said, I'm going to call that X. And Gauss said, well, I know also that whenever you add things up, it doesn't matter what order you add them in, right? Like 1 + 2 is 2 + 1. Doesn't matter if you switch the order. So he just rewrote the list backwards. He said 100 + 99 + 98 plus, and then the very last number would be 1, right? And then he said, okay, if I look at this list on top, the number before 100 was 99, the number before that was 98, and on this bottom list, the number here was 2, and the number in front of that one was 3, and then it goes backwards, right? Everyone good with that? Now here comes the genius, all right? Gauss said, I'm going to add these 2 up. So he said, look, if I add down here If I have something I don't know, X, and I add it to something I don't know, X, I should have two of those. So 2X equals, add just those two together. What do you get?
101.
101 plus add these two together. What do you get?
They're all gonna equal 101.
They're all 101s, aren't they? All of them are 101, all the way down the list. Keep going, all the way to the last one, 101. How many 101s do you have? How many of them are there?
100.
There's 100 of them, right? There's 100 of these. And when you think about what multiplication is, right? If I were to ask you to do 5 plus 5 plus 5 plus 5, right? I'm asking you to add 5 together 4 times. The short way of doing that is just do 4 times 5, right? That's what multiplication is. Multiplication is repeated addition. So Gal said, oh, okay, well, this is just 2x equals 100 101s. And then he said, but wait a minute, that's twice as much as what I wanted. So he just said, I'm just going to take half on both sides. And so you get x is equal to 100 times 101 over 2. Does that make sense? Pretty clever. So I showed you that because most people can follow that, all right? But I lied to you because that's not the way Gauss did it. He was too smart to do it this way. Okay, that's just so everyone can follow me. Here's the way he really did it. He said, I'm going to come up with a formula. So I'm going to add up 1 plus 2 plus 3, but I'm going to stop at n. Not at 100, I'm going to stop at n. So the number right before that would be 1 less than n. And the number right before that would be 2 less than n, wouldn't it? And go all the way, it would go backwards like this. Does that make sense? So if like this is 100, that's 100 minus 1, that's 99. That's 100 minus 2, that's 98. Then he wrote it backwards. N plus n minus 1 plus n minus 2 plus all the way down to 1. 1 in front of that's 2. 1 in front of that's 3. Make sense? It's the same thing I just did. And then he added down. 2x equals, if you just add these two together, you get what? N plus 1, right? If you add now these two together, you're doing n minus 1 plus 2, right? Which is another n plus 1. And then if you do these two together, that's n minus 2 plus 3, another n plus 1. All the way down the list to the very last one, right? Add those two together, n plus 1. How many of them do you have? Not 100, how many? I didn't hear that, sorry, what?
N.
N, you have n of them, don't you? You have n plus 1s. So twice what he was looking for is n plus 1s. And then you divide by 2. So I like to share this because, well, when we're learning about elimination, I want you all to understand that it came from a mathematician that was a genius, absolutely brilliant mathematician. Gaussian elimination is just one of his many accomplishments. This is the level of his thinking in kindergarten. Just, I mean, you have to put your head around, wrap your mind around that for a minute. This is like, 6-year-old maybe, and able to deduce this on their own. Pretty amazing. I always say that this is what separates us mere mortals from geniuses. Like this is genius. This is what genius looks like at 6 years old. But in what's I think is so great about is that it's not that far off, right? It's like most students can follow it. Could you have ever come up with that on your own, right? That's a different thing. So it's actually really cool. All right, it's 2:33. Your homework, that was just, look, I don't want this to be useless information to you. If I asked you on a test as a bonus question to do 1 + 2 + 3 all the way out to 73,461, right? If I asked you to do that, you now have a formula to do it, right? You just plug 73,461 in here, and there you go. I call this the birthday formula, the birthday cake formula. Because if you think about, like, let's say that every birthday you've blown out candles on your cake, right? Let's say you've done it for every birthday. So on your first birthday, you blew out 1 candle, right? On your second birthday, 2. On your third birthday, 3. Then if you're, 32 years old, you could figure out how many candles you've blown out by using this formula, right? Not that that's important, but I'm just saying anytime we need to add up integers, we have a formula. And there's formulas for other things too. If you want to add up, if you want to add up instead of 1 + 2 + 3 all the way to n, we have a formula for that. If you want to add up the squares, 1 squared + 2 squared + 3 squared + 4 squared, there's a formula for that. And then if you want to do the cubes, there's a formula for that. And so we've got all these weird formulas. All right, your homework is to do those odd problems here. And then also from last class to do those 2 remaining logistic problems. And that's it. I'm saying like 95, 98% that I will be on campus next week. Okay, unless something goes really wrong, I will be there. All right. Y'all have a great weekend.
All right, thank you.
Thank you. Have
you.
a good weekend.
Bye,
Take
Travis.
care. Thank you for your understanding this week.